Okay. Hello, everybody. My name is Piotr Bartman. I'm from Jagiellonian University. And today I'm going to talk about my experience from developing Python package for Monte-Carlo simulations in Aurora Cloud Rain microphysics. I will focus on the aspect related to GPU computing. Let me start from short introduction of myself. I am the PhD student in computer science at Jagiellonian University in Krakow, Poland. In fact, it's one of the oldest universities in the world. Before I will say something about software, let me first introduce some scientific context. Generally, one of the biggest challenge in cloud simulations is enormous range of scales from micrometer size particles to kilometer size cloud field structures. And in the simulation, the smallest particles is more than 1,000,000 times smaller than the biggest ones. And here we can see how big is the cloud in comparing to the common ship. And here we can see example simulation. It's a toy example of stratocumulus and Virga phenomenon. The domain has 1.5 kilometer per 1.5 kilometer, and the computational grid is 128 per 128 cells. And the number of computational particles is more than 2 millions. On the left side, we can see the aerosol particle concentration. We see the form cloud base, and the aerosol particle concentration is much higher under the cloud, and in the cloud is near to zero. On the right-hand side, we can see the portrait of mean radius. Time step in this simulation is 1 second, and each time step on this presentation is 2 minutes. On the right side, we can see the drizzle, and on the left side, we can see the aerosol washout. In this simulation, we have 3 main processes included: condensation, which models cloud droplet conditional growth based on the ODE system, advection and sedimentation responsible for air and particle transport, and the coalescence, which models cloud droplet collisional growth with Monte-Carlo algorithm, on which we will focus during this talk. Of course, first and foremost, we expected from our simulations correct results, proper results. But from my perspective, there are some more needs related to modern scientific computing. First, Pythonic, and it doesn't mean that we want that all code should be in Python. For me, it means that readability and the author's intention, what should be done, is more important than details how we do this. Let me notice that code is read much more often than it is written. Colab friendly, and again, it doesn't mean that Colab is something special, but it means that we want to be able to run some sample simulation on, let's say, clear environment, fresh environment, without any manual configuration. So running simulation should be automatic as possible. And GPU enabled, more and more computers, and I mean both personal and supercomputers, has available GPU. But a lot of us still write only CPU code, and not because we don't have access to GPU or because we don't want better performance. The reason is that many of us are convinced that GPU programming is hard and low level. Today, I want to show that it's not necessarily true. Now I introduce super droplet method and our implementation of this algorithm by SDM. Here we have the plot of evolution of particle size due to collisional growth. On the x-axis, we can see the particle radius, and on the y-axis, we can see the dm, where m is the mass over d of logarithm of radius, and the integral over some interval is equal how many water are contained in droplet with radius within this interval. And collision is where two or more droplets collide, merge, and create a bigger one. And during the time, droplets collide, and we can observe bigger and bigger ones. And this is exactly the evolution of size spectrum due to collisional growth. It is impossible to track all particles in the cloud, so we introduced superparticles. Superparticle is a computational particle, which is assembled of some number of real particles. For instance, one superparticle can represent 1 million of real droplets with the same properties. Collisions was hard to model in probabilistic particle-based simulations due to computational complexity O of n squared, but Shima in 2009 proposed SDM, the Monte-Carlo algorithm with linear computational complexity. Generally in SDM, instead of taking all possibilities of collision, we compare n over 2, where n is the number of superparticles pairs, with upscaled probability, and we collide all droplets from one computational particle with the droplets from the second computational particle or nothing. So it's something like all or nothing algorithm. PySDM is a new Pythonic implementation of SDM, which enables CPU and GPU parallelization, one of them. The package core is a Pythonic implementation of super droplet method, and hence the name. In our publication, Super Droplet Kernels, backend level routines for Monte-Carlo particle calculation solvers, API proposal with CPU and GPU implementation in Python, we extract computational heavy parts of SDM, which is alternative to the mean field formulation of Smoluchowski equation, and compare CPU and GPU parallelization performance on real-world problem. In the core of PySDM is two alternative parallel number crunching backends available: GPU resident backend built on the top of ThrustRTC and multi-threaded CPU backend based on Numba. Both of them are similar to runtime compilation and use similar runtime compilation and just-in-time compilation. ThrustRTC is for GPU parallelization and do not support NumPy arrays, in contrast to Numba CPU backend. Compiled Numba code is circa about 100 times faster than pure Python, and is comparable with C++ code. Performance of Thrust will be shown in the end of this presentation. It's a conceptual draft of PySDM architecture. It's convenient to use PySDM from Jupyter-like common package as a, let's say, front-end. To implement microphysics, we can focus most on solving equations and handle physical processes in pure Python code, and not on the technical details. And it's possible by using the PySDM core API. We can even use external packages for some processes, for example, PyMPData. Rest of the work is done by backend. It handles compilation, optimization, and parallelization of Python code. all data is backend resident, so it means that the data is not transferred between Python interpreter and accelerator. We, as output from backend, we have only reductions, for example, the mean size in the cell of particles. PySDM is a Python package using GitHub. Is a Python package hosted on GitHub. It's open source, and we ensure continuous integration using GitHub Actions, Travis CI, and Upveyor. We also use the Jupyter Notebook to provide interactive examples of usage and Binder or Colab to host them. It's alternative. Next section is devoted to ThrustRTC and CURandRTC. To explain what is the ThrustRTC, I want to first say something about Thrust, which is C++ parallel programming library from NVIDIA, mimicking STD algorithm of the C++ standard template library. With Thrust, we can use host or device GPU vectors together with its ready-to-use iterators, reductions, sorting, etc. Thrust is open source and is a part of NVIDIA HPC SDK and CUDA toolkit. And thanks to high-level API, we don't have to have any GPU programming experience to use it. Thrust supports several backends like CUDA, TBB, or OpenMP. So we can run the same code on CPU or GPU by using high-level API. For example, Thrust is optional dependency of Samples subpackage. Despite of the ease of usage, Thrust is so-called template library. It means that it's basically source code that are not compiled until they are used. In GPU programming, templates are especially interesting because of inefficiency of dynamic polymorphism in GPU programming. So if this library is provided in uncompiled form, there is almost no way to reuse them from the language other than C++. And this was the reason why ThrustRTC was created. Similar to Thrust, ThrustRTC is library of general GPU algorithms, but it can be used not only in C++, but also in C interop languages such as Python, C#, or even Java. So since templates complicate things, we can use so-called NVIDIA runtime compilation NVRTC and dynamic instantiation instead of templates. With ThrustRTC in Python, compilation, linking, DLL loading is hidden from the user. We can use automagical data typing and easy pipe installation. In other words, we can benefit from CUDA C++, but without a cost of usage C++. Moreover, ThrustRTC allows us to choose the level of indirection. We can use high-level API, which offers built-in algorithms similar to Thrust, but we also can create our own custom kernels. Unfortunately, we have to use here C++, which we put in Python strings, but still we can decide that we won't put there pure C++ code or Numba-specific part too. And finally, in contrast to Thrust, ThrustRTC supports only CUDA. It's time for some examples. Here we see sorting of Python list on GPU. It's pretty simple. Next, we see reduction, which can count once in our release. The result is 3. Or we can use something more complex. Here we create 3 empty vectors on GPU. Next, we fill one of them with sequence. We have all basic operation available, such as negation, modulus, replace, or arithmetic operations. And to download the data back to Python, we use tohost. Here we compare two simple kernels. First one is the similar to standard CUDA kernel, and second is Thrust for loop. This loop is executed in massively parallel fashion on GPU. Both kernels do exactly the same, multiply array by k. What is important? Implicit typing. For people familiar with Python, it's good news that we don't have to specify the types of our arguments. Moreover, we have C++11 constructs, so inside the kernel, we can use auto before almost every variable declaration. And the difference between a kernel and for is that kernel offers explicit thread control, what is nice to have during optimization of our code. But from the other hand, if only we are not experienced GPU programmers, we can delegate all this stuff to Thrust, which thanks to runtime compilation, tries to find optimal usage for actual GPU. And this is our implementation of coalescence in ThrustRTC. Note that its code is almost valid Python code if only we change some brackets or remove auto. So it's this C++ code is very similar to Python code. So generally, we can start with prototyping our solution with high-level Thrust methods. And if only the performance are not sufficient or the problem is too complex, we can go to lower level by write our own kernel. In our case, it was enough to put some code in the Thrust for loops. We don't use kernels. So you can understand everything, even if you don't have any experience with CUDA programming. Since in our code, there are no information related to CUDA, like number of blocks or grids. Everything is automatically parallel. CURandRTC is a package that depends on ThrustRTC and its simple random number generator. Here we see example of usage in our case. We add layer of abstraction for generating random numbers class random. Note that we can create object with help of CURandRTC in Python and pass it to the defined kernels in C++. To sum up ThrustRTC, we have GPU code with high portability and low entry threshold for developers thanks to high-level parallel API. But there are some challenges. Creating custom kernels is not in Python, but in C++. Some problems with profiling and with maintainability and continuous integration. In our case, we find some hacky way, which we named fake Thrust, to generate code equivalent to kernels, which we can run on machines without the GPU, but it's not the right time for the details. You can find it on our GitHub. It's not a perfect solution, but it works. And now let's play a little and assume we are a reviewer of PySDM paper and we want to reproduce some results. We can go on our GitHub site and we can find there a batch of Open in Collab. By clicking Open in Collab button in our site, we can run one of our demo simulation, our sample simulation via browser. You don't have to install anything. I encourage you to do this after this presentation or during. What you should see after that, here we see the Jupyter Notebook in Collab. First of all, we want to change the accelerator to GPU. It's pretty simple. Next, we wait several seconds for the connection. And first step is to download clone our PySDM repository from GitHub and install dependencies. Everything is done automatically. After running all cells, we can see the resulting plots. And as a viewer, we can play with the parameters or choose computing on GPU or just CPU. And so we need less than 2 minutes to reproduce some sample results and run some simulation from the scratch. On this plot, we can see the comparison. Every point of this plot is the simulation from the demo. On the axis X, we see number of particles, and on the axis Y, wall time of execution. It's not surprising that GPU ThrustRTC backend is faster than CPU backend for large data, but note that ThrustRTC backend is written in Python and pure C++. It's fully portable, readable, and in fact, it doesn't require understanding of CUDA code or architecture. In short, you can, with little cost, leverage GPU in your own software and get 4 times faster code than CPU compiled Numba code, which is 100 times faster than pure Python. It's the orange line is comparable with the C++. In addition, as you can see, thanks to the fake Thrust, it's even possible to maintain continuous integration on GitHub Actions where GPU isn't available for free. Take-home messages. To sum up, ThrustRTC is a portable Pythonic GPU solution with low entry threshold for research developers and users. We have many implemented and ready-to-use algorithms similar to STD algorithms. Thanks to NVRTC, all of CUDA compilation, parallelization, logic, and data typing can be entirely hidden from the user, and is available by seamless pip installation on Linux and Windows. But if it's not sufficient, we can, at any time of development of our software, improve performance by writing less Pythonic algorithms in custom kernels. It is C++ code in strings, but with auto, dec type, and it's similar to Python and work for any data we deliver. We can decide that we want to have everything under control or let something to be done automatically. So we focus only on algorithm, and this is the clue of Pythonicity. And it's CUDA interoperable, means that if we really need to have direct access to any CUDA specific functions inside the kernel code, such atomic operations, synchronization of threads, or access to shared block memory, we have it, but we don't have to use it. And my lesson learned from the developing of PySDM are rapid development of GPU backends offering significant speed up, what shouldn't be ignored in scientific software. There are CUDA-free code with high-level parallelization abstractions. So even if you have no experience with GPUs at all, you still can use the power of massive parallelization in your software. CPU and GPU usage at the same time is to fully leverage hybrid platforms. ThrustRTC by default run kernels asynchronous, so we can still use CPU power while we wait for results. We can create portable GPU-enabled tools runnable also on Colab. And in my opinion, if you run your software on Colab, you probably can run it on most computers. of course, some sample simulation. GPU non-trivial simulation can have high level of reproducibility. In our case, we need less than 2 minutes to reproduce some sample simulation on GPU. And my rule of thumb is if reviewer cannot run your software in fresh environment in less than 1 hour, they probably never do it. In the end, I would like to thank Mr. Fei Yang, the author of ThrustRTC and CURandRTC. And the first link is a link to our paper about super droplet kernels. And next is the link of our GitHub of our group and PySDM. Thank you for your attention.